Good afternoon. I welcome you to this session of experimental methods in fluid mechanics. Today we will start our discussion on flow measurements, and in this module we will be discussing flow obstruction flow rate measurement, and then we will see that how we can measure using drag. In fact, the flow obstruction flow rate measurement technique which we will be discussing today. This part we have studied in our undergraduate fluid mechanics part, but we will try to recapitulate and we will try to discuss a few critical issues while we are using these instruments to measure flow rate, and then we will discuss that how we can measure flow using another instrument which is known as rotameter, where we will be using drag. Now, the flow rate measurement is considered to be the measurement of volumetric or mass flow rate through dark or any fluidic confinement, or it may be a point velocity measurement and determination of flow streamlines. The measurement of volumetric or mass flow rate is common, rather I can say is the common by far, and has many engineering applications to define thermodynamic and chemical processes, and also the accurate flow measurement is important in different commercial applications. In fact, I can tell you that when we talk about flow rate, rather flow measurement, flow rate, the mass flow rate or volumetric flow rate is very important quantity irrespective of the length scale of the system which we are considering. Almost over all the length scale, the volumetric flow rate or mass flow rate is of immense interest, because that is what we need to consider while we are designing those devices, any particular device for many applications, say starting from macro to micro, whether it is pipe or it is channel or it is miniaturized systems or devices, where we need to focus our attention while designing to check whether that system device will provide the desired flow rate or volumetric flow rate or the mass flow rate. Now, because of this, the volumetric flow rate or mass flow rate measurement, rather I can say, is important by its own right. On the other hand, as I said that the flow measurement is considered to be three different aspects. So, I can write the flow measurement is considered to be the measurement of volumetric or mass flow rate, number 1. Number 2, it may be point velocity measurement, or it may be the determination of flow streamlines. So, when we talk about flow measurement, we are considering either the measurement of volumetric or mass flow rate, that is very common, as I said, it finds many applications, engineering application to be precise. Then second is the point velocity measurement, and third one is the determination of flow streamlines. Now, the volumetric flow rate or mass flow rate, as I said, we have studied in our undergraduate fluid mechanics course. There are many instruments which are used to measure the volumetric flow rate. In particular, just now I have said that flow obstruction flow rate measurement, I will be discussing this part today, and other is the second one is the point velocity measurement, which is measurement by research. This is very important as a research type measurement. I can say the number 2, this is typically a research type measurement. So, the point velocity measurement is typically a research type measurement. I can say ki measurement exception is there that we cannot measure the speed of the aircraft. So, exception I can write is the measurement of aircraft airspeed and third one, determination of flow streamlines. It has a long and productive history and we will try to briefly touch upon it. So, we have discussed that flow measurement which can be considered as the measurement of the volumetric or mass flow rate, number 1. Number 2, point velocity measurement, which is typically a research type measurement except the measurement of speed of air or aircraft airspeed, and last one is the determination of flow streamlines. Now, see today we will be focusing our discussion on flow measurement, that is the measurement of volumetric and the mass flow rate. So, this flow measurement that is volumetric or mass flow rate measurement. So, we will be focusing on this part today and we will see that how, in fact, we have seen in our undergraduate course fluid mechanics course that this is called flow obstruction flow rate measurement, whether it is volumetric flow rate or mass flow rate. So, flow obstruction flow rate measurement, that means we have seen venturi meter, orifice meter that we have studied in our undergraduate course fluid mechanics course. Now, we will briefly discuss today, rather we will recapitulate those. Now, so if I now start our discussion, flow obstruction flow rate measurement. Typically, devices, instruments which are used to measure flow rate following the principle of flow obstruction. In fact, I can say those devices or instruments works on the principle of the fact that obstruction of any shape, if it is placed in the flow field, then it will leads to a rise in the pressure difference, pressure drop, and if we measure the pressure drop, then either through empirical relationship or analytical calculation we can calculate the flow rate, and that is what we have learned. So, the instruments, as I said, venturi meter, say venturimeter, orifice meter. So, these two devices, instruments working on the principle that obstruction of any shape, if it is placed in the flow field, then it will, the placing of that obstruction will results in a drop in pressure, and if we calculate the pressure drop using empirical relationship or either using empirical relationship or using analytical method, we can calculate the flow rate, and that is what we have learned. So, I am writing that these meters work on the principle that if an obstruction of any shape is placed in an internal flow field, flow, a pressure drop will be the result. Now, if we can measure the pressure drop, then using rather measuring that pressure drop, we can calculate the flow rate, and that is what we know, and today I will try to outline those calculation, not in a greater detail, but we will try to discuss briefly. So, then this is one, and then two, then either analytical calculation or empirical means we should be able to measure flow rate by using the measured pressure drop. So, by measuring pressure drop. So, this is the outline, rather the principle of using flow rate, using the flow obstruction flow rate measurement instruments. We can start our discussion. In fact, as I said, I won't be able to discuss, rather I won't discuss this aspect in a greater detail, rather I will discuss in a briefly to just to outline and in fact to recapitulate what we have learned. So, see, if we start using venturimeter, in fact I will discuss only one instrument, venturimeter, which is used to measure flow rate. So, which is used to measure flow rate. So, we know that venturi, which is used at least to have a drop in pressure of the in the flow field. So, if I try to draw the schematic, which is very simple. So, this is the incoming flow and say this is center line. There are 3 different parts that is clearly seen from the schematic. This is throat, and there are one is convergent part and other is the divergent part, and this is the pipe diameter d. So, this is the flow direction. So, this is divergent part and this is convergent part and the diameter, the pipe is connected to the convergent part diameter d, and this angle say alpha 1 and this angle is alpha 2, and diameter of the throat is small d. So, d small d is the throat diameter, capital D is the pipe diameter at the inlet and outlet. So, this is pipe at the outlet D, pipe dia at inlet comma outlet, and the alpha 1 and alpha 2, these two are the angles. This alpha 1, these two are the the cone angle, and these angles are the angle of the convergent and divergent part, that is near about 20 degree plus minus 2 degree, and this is alpha 2 is equal to 5 degree plus 5 to 15 degree, I can say 5 to 15 degree. Now, this is the flow direction. So, this is incoming flow and this is the outgoing flow. So, this is the schematic we have we have seen, we have studied many times. Now, this is flow obstruction flow rate measurement, that means the throat is provided. So, this is a kind of obstruction. So, the pipe diameter d which is there at the inlet and outlet, but the pipe diameter d which is connected with the convergent part and the same pipe is connected with the divergent part, in between we have a flow obstruction. So, we have a venturi kind of thing. Now, so this venturi is used to provide rather a pressure drop, I can say ki this when flow is approaching to the convergent part, then velocity, the streamlines will follow the geometry of the nozzle, rather convergent part of the that section of the venturi. Now, when flow is approaching towards the throat, streamlines will be deflected towards the center, and then again when the flow is coming out from the throat and towards the approaching towards the divergent part, again there will be a change in pressure and velocity, that we know. So, essentially to disturb the flow field, to have a pressure drop, the venturi is provided. Now, measuring the pressure drop, that we need to connect pressure tapping between throat and the, we have seen that we need to connect a manometer between the throat and the upstream of the throat, that is within the convergent part, and that there are some issues that the pressure tapping should be connected at least one diameter ahead of the one tap will be taken from the convergent part, but which is one diameter one throat diameter ahead of the from the throat, and at least 0.5 diameter downstream of the throat towards the divergent part. And this is done normally to check whether, because if the streamlines are not parallel to each other, then the measured pressure drop using the manometer should not be the correct one and we may not get the correct result. So, to ensure that the streamlines are parallel and the measured pressure in the flow stream, measured pressure from the flow stream is the actual pressure, to ensure that these precautions are taken, that the pressure tapping should be taken, connection should be taken, this location in the convergent part and that location from the divergent part, that is the condition. Now, the measurement of pressure, this is very straightforward, we can get it from the U-tube manometer by observing the height, differentiating the manometric liquid height, and then by doing some simple algebraic calculation we can calculate the total flow rate, rather which is flowing through the duct rather through the pipe. And this simple calculation we have studied in our undergraduate days. Now, but this simple calculation we need to know our fluid mechanics understanding, which we have learned, that continuum conservation equation, that is mass conservation, and then we should apply the if we consider the flow is incompressible, then and we can apply the Bernoulli equation, but we will discuss that we can apply Bernoulli equation if the fluid is inviscid, but it is not really the case. So, one correction factor should be taken into account, because of the frictional losses the measured pressure should not be equal to the pressure drop that is there actually in the system. So, conservation of mass, that is m dot, that I can write rho v dA, A, that is rho into u into A is equal to constant. Conservation of mass, which requires that the flux through any cross section of the tube is constant. So, this requires that flux through any cross section of a tube to be constant. So, that is we have written in terms of mathematical expression, where rho is the density and u is the appropriate mean velocity respectively. Now, where I can write rho is the density and u, see if I apply conservation equation, we can write rho times velocity times area times is constant. So, rho times velocity times area is constant, and this simplification of the mass conservation equation is based on the assumptions that the velocity is uniform on that particular cross section. Density is not changing, because if you consider incompressible flows, we are considering density is not changing from one cross section to other cross section. Definitely cross sectional area will be changing, but the mean velocity, the velocity which is taken mean over that cross section, and that is one of the important assumptions of this simplification. So, that is the mean velocity. Now, if I write the Bernoulli equation, because we can apply Bernoulli equation in this case only under the assumption of that flow is inviscid. So, initially we are considering flow is incompressible and then we are considering is flow is inviscid, but this is not the case, because this is not the case, but we are taking these assumptions essentially to apply Bernoulli equation, from where we can calculate the drop in pressure theoretically, and that drop in pressure if we equate with the measured drop in pressure from the manometer, from there we can calculate the velocity and then subsequently the flow rate. Now, applying Bernoulli equation, if I apply boundary condition between two sections, that means one section that is at the middle of the throat and which is upstream of the throat, and that is what I said, that the location of tapping should be taken carefully, so that in those locations streamlines should be parallel to each other. So, because of the curvature effect of the streamline, the pressure will not be the actual pressure that that we are going to measure. So, now if I apply boundary equation, I can write P1 by rho 1 plus V1 square by, rather I can write U1 because I have taken U. So, I am writing U1 square by 2G is equal to P2 by rho 2 plus U2 square by 2G. And from there, in fact, I am not going to write that. As we consider incompressible flow, in fact, I am considering density is also constant. Density constant is a special class of special outclass of incompressible flow, but fine, for the time we are considering the flow is incompressible. That does not mean that density will be constant. Density may change in space and time in such a way that the total effect will be I mean substantial derivative will be 0, but we are going to consider that the density is equal to constant. And if density is constant, then we can write that U2 square minus U1 square, that will be equal to U2 square into 1 minus A2 by A1 that square, and this is nothing but if I try to write U2 square is equal to, because for constant density flow from the mass conservation equation I can write rho A1 U1 is equal to rho A2 U2. From there we can write that U2 square minus U1 square is equal to this, and this is nothing but from Bernoulli equation we can write this is nothing but twice by rho into P1 minus P2. So, this is U2 square minus U1 square. So, this is U2 square minus U1 square, that is nothing but 2G by rho into P1 minus P2. So, that is we have obtained. So, now this P1 minus P2 delta P that we will get from our experiments, that is by we have by since we need to connect manometer between these two points. Now, I can write from that equation U2 will be equal to 1 minus the straightforward formula that we have studied many times, 1 minus A2 by A1 square root of twice by rho into P1 minus P2, that is delta P. So, knowing the velocity, this U2 is the velocity. So, if we go back to my previous slide, this is at the upstream of throat, and this is at the throat. So, this is at the throat. So, U2 is the velocity of flow, rather flow velocity at the throat. If we know the cross sectional area of the throat, we can calculate the volumetric flow rate cube, that is U2 into A2, and that is nothing but A2 by root of 1 minus A2 by A1 square root of twice delta P divided by rho. So, this is the volumetric flow rate we have this is Q dot I can write. So, that we have calculated. Now, this is very straightforward, and we have studied this. Only thing is two important points that I have written in the beginning, that this flow obstruction flow rate measurement techniques, because venturimeter, orifice meter, and also we will see that another rotameter which works on the principle of drag, which is the flow drag. Now, the flow obstruction fluid measurement, the venturi meter and orifice meter, these two meters works on the principle that if an obstruction of any shape is placed in an internal flow field, that obstruction will leads to a drop in pressure, and if we can measure the drop in pressure, from there we can calculate the velocity, and from there we can calculate the flow rate. That is what we have seen. Now, these aspects are also detailed in undergraduate textbooks, in most of the undergraduate textbooks, that when you are connecting, when you are taking pressure connection to measure the pressure from throat, we need to ensure that the pressure tapping should be connected from pressure tapping should be taken from those locations where streamlines are perfectly parallel. Because of the deflection of the streamlines, the measured pressure may not be the correct pressure. So, the our entire calculation measurement may not gives us the correct result. And this is what the schematic of the typical venturi. I am not going to discuss in detail, because this aspect has been discussed in most of the undergraduate textbook, where the constructional feature, their geometrical shape and all those things are described. But only thing is that we have considered two assumptions: the flow is incompressible. So, again I said that flow incompressible, that does not mean the density has to be constant, but we have considered density is equal to constant. A variable density flow might be incompressible. So, incompressible flow will be the incompressible flow means density constant. It is not the case, but we have considered density constant. If we consider density constant by applying mass conservation equation at two sections, we can calculate the velocity. Now, the change in velocity between these two sections can be correlated in terms of pressure drop, that is obtained from Bernoulli equation, and we are applying Bernoulli equation forcefully because fluid is not inviscid at all. But one of the most important assumptions of applying Bernoulli equation is that the fluid has to be inviscid. But applying that Bernoulli equation, if we can calculate pressure drop and we can relate pressure drop in terms of velocity field and velocity change, and ultimately we can come up with the flow rate at the throat. Now, since we have considered two assumptions, the first one is not that much problematic for this analysis. Density will be more or less constant for the incompressible flow. Now, since we have considered inviscid flow, but in reality fluid is not inviscid because of the viscous effect, fluid layer, there will be a frictional effect between the fluid layer. So, that effects will leads to mismatch in the measured pressure that we are getting from the U2 manometer. So, the flow rate that we are getting from this formula is not the correct one, and that is should be multiplied one factor. So, this Q actual, so this is ideal case because we have considered the fluid is inviscid, but in actual case the flow rate will be slightly less than the actual one, and that is multiplied by one constant, that is coefficient of discharge into Q ideal. And this is close to 1, that is experimentally proved value, typically from 0.9, 0.92 like this. So, from there we can calculate the actual flow rate of the internal duct, and this also can be applied in any other fluidic confinement. But two important things is that the measured flow rate is not the correct actual one. To obtain the actual value, we have to multiply it by the CD, and the CD we have to obtain from the literature. Now, this is all about the incompressible flow rate measurement. So, as I said in the beginning of my lecture, that flow rate measurement can be considered to be the measurement of flow or volumetric or mass flow rate in first one. It is always not the case that flow measurement is only the volumetric and flow rate measurement, but since our discussion today is focused on the flow rate measurement, means the volumetric flow measurement is the rather today's discussion is focused on the volumetric flow rate measurement or the mass flow measurement. So, we have discussed that part only today, and we will see that even if we focus on the volumetric or mass flow measurement, mass flow rate measurement, then what will, how we can measure the compressible flow, that the flow always may not be the incompressible one, but we need to know if we need to measure the compressible flow, volumetric flow rate of the compressible fluid, then how we can measure. So, that part we will discuss in my next class, and along with I will try to discuss the other things, that how we can calculate the flow rate using the drag. That is what I have told, that we can use drag to measure flow rate. So, measurement of compressible flow in an internal duct along with measurement of flow using drag, that part we will be discussing in the next class. Thank you very much.